This video will discuss using XProps in LabView. To begin, we have created a new VI file. These files have two windows, the block diagram window, which we are currently in, and the front panel window, which we will move to later in this video. The main difference between these two windows is that the block diagram window represents what's going on within your LabView program from a programming perspective. It uses graphical blocks and wires to show the connections between inputs, outputs, and functions in your LabView project. The front panel window, on the other hand, acts as the front interface for you when executing your code. It's where you can actually type in any inputs and will see any outputs. It also has a mix of graphical items and text. To use XProps in LabView, we will need to access a specific file within the XProps installation folder. This file is a DLL file, which is an external library. We use this specific file in the XProps folder because LabView has, built into its system, an ability to utilize functions from an external library. We will need to connect that file to our LabView interface. To do that, first we will go to the search bar right here with the magnifying glass and start typing call library. As we type, this drop-down menu should appear, and in the palette section, we should see an option called Call Library Function Node with a yellow triangle similar to the LabView icon. Select this option and drop the little graphic somewhere in the center of the block diagram page. This graphic is the Call Library Function Node graphic, and what it does is it allows you to call an external library and access its functions within LabView. This graphic is actually a graphic of a table, which is hard to see right now because it just has its header and one row, but as we fill in more information, more rows will appear. What we're going to do is double-click on the icon, and now a menu should appear with Call Library Function at the top. This menu has four tabs: the Function tab, the Parameters tab, the Callbacks tab, and the Error Checking tab. We are going to leave the last of these two tabs, the Error Checking and the Callbacks, at their default settings. The Function tab is where we actually summon the external library and select its function that we wish to use. In the first box here, library name or path, is where we can either physically type a path on our device to the external library of our choice, or press the folder icon to navigate to the XProps folder, the x86 folder, and the file XProps LBV.dll. The LBV stands for LabView. We can select this file, and now, in this box, we should see the path on our device to this exact file. If we choose, we can check this box to specify that path on the diagram, but this is not strictly necessary. Going to the next box is the function name. Here we have a drop-down menu which lists all of the available functions encoded in the XProps LBV.dll library. There are four functions, each with their own inputs, outputs, and requirements. These are similar to the XProps functions that you can use in MATLAB, MathCAD, or many other platforms. We are going to demonstrate using the XProps_get PTX function. The remaining two boxes on this tab we are going to leave at their default values. Another thing to notice is that no matter which tab you navigate to, at the bottom is this box called Function Prototype. This essentially acts as a preview for how your function that you are currently building is supposed to work. Right now, when all you have entered is the path to the library, it should say void XProps underscore get PTX with another void in the parentheses. This first void is the return type because in the external library, this function is not coded to specifically return any value. It merely prints a list of a bunch of outputs. Then it has the function name, which is XProps underscore get PTX. And then in the parentheses, it has any parameters that we are passing into the function. Because we have not added any parameters yet, this should say void. But as we add more parameters, you should keep an eye on this box and see more values replacing this void inside the parentheses. Now that we have entered the library path and selected our function, it is time to input the parameters for our selected function. The getPTX function takes 4 input values and gives 6 output values. The 4 input values are, first, the refrigerant name and units, which together form one input unit. Second, an integer, which tells us which combination of pressure, temperature, and quality the third and fourth inputs will be. The outputs for this function are either a saturated temperature or pressure, depending on what combination of pressure, temperature, and quality make up the inputs, a specific enthalpy, a specific volume, a viscosity, a thermal conductivity, and an error. We can add all these inputs in the Parameters tab. Currently, the only parameter present is a return type, which is void, because, as previously mentioned, this function does not explicitly return a value. To add a new parameter, you press the plus button, and to delete any existing parameters, you press the X. You can move parameters up or down, but their order is not really that significant. For each parameter, you will assign it a name, a type, which is a general data type, such as numeric, array, string, and more complicated data types. You can note if this value is constant, and then not only do you have to select a general data type, but there are also more specific data types for each type of data. For instance, numeric data can be represented either as an integer or as a double. Those are the two options we will use in this example. The final category for each parameter is the pass selection. What you select here will determine whether your parameter is an input or an output. Inputs pass values, meaning you will enter a value as your input and then that value will be passed to the program. Outputs pass pointer to values because the program is what calculates the value and then that value is just represented with the output. As mentioned before, our first parameter is going to be the refrigerant name and units. This data type is a string, and unlike the rest, will be constant. The C-string pointer is fine, and it does not have a minimum size. As you can see, once we've started adding this, it appears below in the parentheses, replacing the void. The next input, also as mentioned, is the special integer, which will tell us whether our third and fourth inputs are pressure and temperature, temperature and quality, or pressure and quality. This is a numeric type of parameter because an integer is what represents the parameter selection. We will leave it as a signed 32-bit integer, and we are passing a value because this is an input. Our next inputs are the combination of pressure, temperature, and quality that we indicate by the value we use for the param type variable. These two are virtually identical, so I will call them input 1 and input 2. They are both numeric, but because they are representing either pressure, temperature, or quality, they're going to be doubles rather than integers so that decimal places can be included. At this point, we have finished making parameters for all of our inputs. However, in order for our function to work, we still need to create parameters for all of our output values. 5 out of the 6 output values are nearly identical because they are all returning physical properties. It is only the error code that is slightly different. Because we create all the parameters in the same menu, I like to designate output variables with the name out. Although our first variable can be either a saturated pressure or temperature, for space purposes, I usually just call it saturated temperature. It is numeric, but will be a double. And here, most importantly, instead of passing a value, we need to pass a pointer to value because this is an output. This is noted below by the little star before the name. Next, we can create specific enthalpy, specific volume, which we can call just V for simplicity, thermal conductivity, viscosity, and now we are ready for the last output value, which is our error. What the output error does is it essentially outputs a string of integers that lets you know that you have an error. It does not need any decimals, so we will leave it as a signed 32-bit integer. But it does still pass a pointer to value. If you look at the function prototype box now, all of the parameters listed here, except for the return type, should be present in the parentheses, with anything that passes a value simply having its name and data type, and anything that passes a pointer to value should have a star before its name. Once you have selected all the parameters, press OK. At this point, when you are back on the main screen of your block diagram, you should see that your little table now has the same number of rows as parameters that you created. Each row has a code that indicates the data type of the parameter. ABC represents string, I32 is a signed 32-bit integer, DBL represents double. These are also color-coded with strings being pink, integers being blue, and doubles being orange. Now that we have entered all of the parameters onto the block diagram, it is time to move to the front panel. As mentioned before, the front panel is the interface we use to actually input our values. There is a lot of organization that we can do with the front panel to keep it useful. One of the main things is that, like on the block diagram window, double-clicking anywhere will allow us to type. We can also make use of our normal keyboard shortcuts, whatever they may be, to have bold, italicized, and underlined text. No matter how much organization you would like to do, the first step is to go to the View tab and select the Controls palette. The Controls palette is the palette we use that both contains the tools we need to actually create our inputs and outputs, as well as some organizational tools. I'm going to take a minute to highlight the organizational tool that I use. In this first tab, which is the Modern tab, I like going to the Decorations folder, which has all the shapes on it, and choosing some of these boxes. I generally put one box for all of my inputs and another for my outputs. These boxes can be copied and pasted. I use them as a way to keep all of my inputs and outputs in the same place. Now, we are ready to start actually creating inputs and outputs. We are going to stay in the Modern tab, and if you mouse over the folders, you will notice that some of them had types that were similar to those that we saw on the parameters page. The ones we will be using are the numeric folder and the string and path folder, because all of the parameters that we have created are either strings, or numerics. Within each of the folders, there is usually a selection of options, but the two that we will actually care about are the controls and the indicators, which are generally the first two options in any folder. Just like in the Parameters tab, how we designated each of the parameters we created to either pass a value or pass a pointer to a value, and that designation made them either inputs or outputs respectively. Here, creating anything as a control will designate it as an input, while creating it as an indicator designates it as an output. There are some minor visual differences between the two that we will explore as we add our controls and indicators to these pages. It does not matter what order the controls and indicators are added in. For us, we're going to go in roughly the same order that we added the parameters, doing all of the inputs first, then moving to the outputs. As you recall from the Parameters tab, our first input was the refrigerant name and units, which was a string. So we are in the String and Path folder, and we will select String Control. A little box will appear with a smaller box on top that we can drag and drop anywhere we want on the front panel. Once you drop it, there should be a white box with room to enter text and a label on top of it. Here is where I usually type out the full information about what this control actually is. What this control actually is where you will enter the refrigerant name and units code for this function. For the refrigerant name, you may select anything from the RefProp database because that is a database that XProps uses. For this example, I will use R134A. Following the refrigerant name, you add a comma and then add the units code. This function takes in either modified SI units or English units. Modified SI units differ from SI units in that they use kilopascal for pressure and kilojoules for energy, as opposed to regular pascals and regular joules. Modified SI units is abbreviated MSI, while English units are abbreviated ENG. For this example, I will enter my values in MSI units. Now we are ready to go to the next input. All of the remaining inputs and all of the outputs will be numeric rather than strings, so we navigate back to the main Modern tab with all the folders and select numeric. As you can see, there are a whole host of fancy options, but again, we will stick to just numeric controls and numeric indicators. While for strings, the control and indicator look virtually identical, the big visual clue that indicates whether you are placing a numeric control or a numeric indicator is that numeric controls are set as their defaults to have an increment-decrement button. Although you can hide this button, it is a good visual check to make sure that you are using controls and indicators in the respective appropriate places. Our remaining three inputs will be numeric controls. The first of those is the parameter type. As we discussed when we created the parameter type input takes one of three integers, 0, 1, and 2. That integer will indicate to us and to the program what combination of pressure, temperature, and quality the remaining two inputs represent. Because it takes in such specific values, we're actually going to modify the control a bit to make sure that we don't run into any unnecessary errors. To modify the control, right-click on it and press Properties. The first tab in the Properties folder is the Appearance tab, where you can get rid of this increment-decrement button, as mentioned before. The important tabs will be Data Type and Data Entry. Data Type at the top has a representation that tells you what kind of data this input is expecting. Here it is set to double, which we need to change, because if you recall, on the Parameters tab, we had assigned the parameter type to be a signed 32-bit integer. If we leave the representation here at a double, we will get an error because it will be a mismatched data type. To change the data type, press the box with DBL in it and select I32 instead. Selecting I32 is important because in the Parameters tab, we had assigned it as a 32-bit integer. The next thing to do is to go to the Data Entry tab. As you can see here, it is checked to use default limits. If we uncheck this, we can see that the default limits are set to a rather large range, which, for most numeric controls, is perfectly adequate. But, as mentioned before, the parameter type only takes in 3 very specific integers, so we're going to reset the limits to prevent it from taking any others. Because those 3 integers are 0, 1, and 2, we set the minimum to 0 and the maximum to 2. At this point, we are done modifying the parameter type control, and we press OK. Now, when we actually go to type in, if we type in 0, it tells us that input 1 is pressure and input 2 is temperature. If we change that to a 1, it will tell us that input 1 is pressure and input 2 is quality. And finally, if we change this indicator to a 2, it tells us that input 1 is temperature and input 2 is quality. We only have these 3 options because it is important that each option from pressure, temperature, and quality is paired with each other option, but the order of that pairing is not relevant for this program. The order of that pairing has no bearing on the outputs, which is why we only have those 3 integer options. Now, we are ready to create the input 1 and input 2 controls. Like when we created them as parameters, the process is virtually identical. We simply click Numeric Control again, label them, and are done. Because we created these as doubles, because they will be representing either pressure, temperature, or quality, they should be doubles because those can often include decimal places, and they can have a large range. One thing that is important to note is that there is no visual indication of what input 1 and input 2 are actually representing. From just looking at them, there is no way to know whether they are pressure, temperature, or quality. Therefore, it is extremely important to understand what you enter into the parameter type control and know what that represents. At this point, we are ready to start creating outputs. The process for creating outputs is extremely simple, since only the error output, like with the parameters, differs from the others and will require any modification. The big difference here is that instead of selecting a numeric control, we select a numeric indicator, because these are outputs. We can place the outputs in any order. What is important to note about the outputs is that, unlike the controls, they do not come with an increment-decrement button. Although we can hide that button for the controls, as mentioned before, it acts as a good check to make sure that we are creating controls and indicators where appropriate. Now we are ready to create the error. This is also a numeric control, but after we create it, we will right-click and go to Properties. If you recall, when we created the parameters, we had created the error as a signed 32-bit integer. Therefore, like with the parameter type control, we need to go to the error indicator and change its representation to I32. Once you have done that, your front panel should be fully operational and ready to input any values. Once we have finished adding all of the controls and indicators on the front panel, we can return to the block diagram window. In that window, we should see all of these blocks with the same names as the controls and indicators that we added, sprinkled around the diagram, roughly equivalent to their placement on the front panel page. As you can see, these boxes follow the same color code and labeling as the rows in our central table. The strings are in pink, the integers in blue, and the doubles in orange. Each block is labeled with the same label as the control or indicator that we created on the front panel. Now that we have all of our blocks, we will connect them to the central table so that LabView can process our function. We do this by wiring. Wiring is literally drawing lines between these blocks and appropriate rows in the central table. If you'll notice, each box has a small triangle, either on its right side or its left side. And when you mouse over the central table, triangles appear on each side of each row as well. These triangles are the terminals where the wires go. For controls, the triangles should be on the right side of the blocks, and for indicators, they should be on the left. Because the central table just contains all of the parameters that we gave, it has triangles on either side. What we need to do now is draw lines from the triangles on our controls and indicators to appropriate rows in the box. If we mouse over each individual row in the box, it tells us the parameter that is connected to this row. Although it does not matter what order your boxes are in on the block diagram, it is important to connect each appropriate control and indicator to the parameter that you want it to represent. For instance, the outlet viscosity is towards the bottom here on the table, but it is in the middle of the blocks. We will want to connect the outlet viscosity parameter to the viscosity indicator to make sure that the right value ends up in the right place, even if it leads to messy wiring. To start wiring, simply click on a triangle, either on the box or on the central table, and a dotted line will start appearing. Connect it to the appropriate triangle on the central table, mousing over it to make sure you have the correct one. We are drawing from the refrigerant name and units code control, and so we want the ref name and units parameter. It is also helpful here to use the pink color code. Click again, and now the wire should turn pink. For the parameter type, we'll send it to this integer that's called param type rather than the error. And as you can see, all of the controls are wired from the right of the control block to the left of the central table. Now, for input 1, because it is a double, theoretically, we can wire it into any role of the same data type. However, we want to assign it to the correct parameter, which is input 1. We will do the same for input 2. Now, for the indicators, we will wire them on the right side of the central table and the left side of the blocks themselves. Here we have the outlet saturated temperature or pressure, so we will wire the saturated temperature or pressure for that. The specific enthalpy is wired to outlet H. The viscosity, as shown before, is wired to outlet mu. The specific volume to outlet V. The thermal conductivity to outlet K, and the error to the out error. Now everything is wired. If you make a mistake during wiring, you can click on a wire and backspace to delete it, or if you have a broken wire that's not connected, you can press Ctrl B to delete it. Both of these options are also available in the Edit tab, where you can clean up diagram and remove broken wires. If you wish to add more controls or indicators, you may do so here on the block diagram without returning to the front panel. Simply do this by right-clicking on any of your existing controls or indicators, and a menu will pop up that includes Create Control and Create Indicator. This right-click is also where you can easily change a block to be an indicator or a control. This is useful if you accidentally did the wrong thing on the front panel. Any controls or indicators that you create or change here on the block diagram will be reflected onto the front panel, although they may not follow whatever organizational schematic you had set up. Now, assuming that you have put values into your front panel, you should be just about ready to run the diagram. As an example, as you are creating your diagram, you should notice that there is an arrow up here. When that arrow is gray and fractured, it means that you are not yet ready to run your program. When you mouse over it, it will display list errors, and pressing it will tell you what the errors are. The errors here are that input 2 is unwired, and that there is a broken wire coming from the terminal. If I need something more specific, I can press Show Error, and it will hone in on the issue. Once I fix it, the previously gray and fractured arrow should turn white, and now when I mouse over it, it should say Run. Once the arrow turns white and says Run, it means that you are ready to run your program. The only indication that a program has been run will be if you return to the front panel and see output values in your indicators. If you would like your program to run on a loop, there is a way to do that. Simply right-click anywhere on the block diagram to open up the Functions menu. In the Programming tab, in the first folder called Structures, you can either click or mouse over it and select the while loop. Then, drag all of your existing wiring inside the loop. You will see there is a little stop button in the corner. You will need to wire this stop button to your central terminal. Then, once it is wired and your arrow turns white, you will be able to run the program, and it will run continuously, only stopping when you press this red stop button. For more information on LabView, you can look in the Help tab or type any specific objects into the search box. And for more information on XProps and LabView, you can consult the XProps help file or contact support at optimizedthermalsystems.com.